Good morning.
How are you?
Good. You?
I'm alright.
I started my second math class yesterday.
Okay. What was that?
Finite.
Oh, alright. Taking finite a long time ago.
Yeah. It's like probability theory.
Yeah, finite's pretty different. Venn diagrams, probability, commutations, permutations.
Sounds fun.
It's very different. Yeah, you'll probably like it. There's also some like logic stuff.
Apparently there's something like about programming and stuff in it too.
Well, I don't know about that. Unless you mean linear programming.
It said something about programming.
Linear programming is mapping. It's not like computer programming. If that's what it was, so.
Possibly.
Morning. Make sure you guys grab the handouts and find your new seat number on the board, please.
Starting to do Riemann sums?
We did Riemann sums before break.
Yeah, but infinite Riemann sums this time.
Well, we're showing what the definition of an integral is.
Oh, yeah. I think probably around the eraser. I don't have yeah, I use this one.
Yeah.
That's where I got these, but, and then Douglas, they don't have them anymore. I hope I get a good partner because they're never gonna go again. It's so bad. Exactly. So I just did not wear my glasses.
No, I was talking about it, so I really didn't. I got from the other side of the Like, I saw it, this is forever ago. Yes, I'm going next week. It's, yes, I've heard it. But like, not like an official tour, but like, yeah. Because I looked at the, so their kids like, I could so Esther.
Yeah.
No way.
Yeah.
There's no way.
Yeah.
Oh my gosh.
Yeah.
It's so expensive.
Is that ever happened?
Really? Did you see study? Oh.
Okay.
Yes.
Are your guys'
That, yeah, I rated it.
I swear all out of state schools, you can't really go. When you do get money, it's like at least 50. When
Yeah.
taxes and everything.
Fill out the, like, option stuff. That's currently what I do. And I don't think, I'm not in. They have kids like two. Neither, they're very different. They're not, yeah, that's
That's right. But it sucks that they're cheated out.
Yeah, she's probably wondered. She's like,
Did she get money?
yeah, she said she had, but then she got zero and she
I got a lot of stuff. Yeah. They're both.
I got a lot from him.
It's so weird. It's like almost like what paper you're trying to get, like ethics, there's like money you're supposed to put on song, and then you have to then there's stuff. But who knows, like later on, like they can get you like.
And they gave money to. Oh my god. Were you like,
Yeah, I'm so worked out. I wanna do this.
I'm majoring in fashion, merchandising, and going to law school. Yeah, I kind of like replied to the story, but like there wasn't a bar to do. I was like, dang it, no. That's why you like better. Yeah, I didn't have to do anything. Yeah, I like didn't have to do anything. I didn't do the tour. I like the tour. It's the only one I'm going to.
Yeah, I wasn't going, and it's like, I don't like school that way, so I feel like.
Yeah.
So it's just.
Yeah, that's so real.
It's what it's back here, so we're close to
Like the breakfast movie is literally crazy. Like I ordered it. It's so crazy.
See, Lori's not here today. 1, 2, 3. Thompson.
Good morning, FHS. Today is Thursday, January 4th, 2024. Would you please join me in a minute of silence?
Mr. Freeman. Mr. Brown.
Please stand if you are able and join me in the pledge. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all. Thank you and have a great day.
All right, good morning. Welcome back. I hope you all had a very nice and restful break. Thought we could start off this morning by just giving kind of a general overview of what our semester will look like so that you guys can try to plan accordingly. So we start off with chapter 5. And we actually did a tiny bit of chapter 5 in December. So if you guys remember, we did left, right, midpoint Riemann sums. We did trapezoidal sums. We talked about area under a curve a little bit. And we talked about whether those would be overestimates or underestimates. Technically, all of those are chapter 5 concepts. We just showed them to you a little bit earlier so that there's not so much thrown at you in January. But our first big assessment of the semester will be over sections 5.1 through 5.4. And I like to warn you that this is probably the hardest one of the semester for students, the one that we are going to be starting or continuing on today. So it's not that it's like impossible or anything, but it is the hardest of the semester, in my opinion. After we finish that, we will learn one more topic called U substitution, which is going to be really important. And then we'll assess all of Chapter 5. So it'll assess U substitution and the 5154 stuff. So in theory, I guess that should be harder because there's more content on it, but usually students do a little bit better just because you have an extra week or two to digest that information. So first assessment's the hardest, next assessment's probably the next hardest. Then we go on to Chapter 6, but there's only like 3 things you need to know from Chapter 6, so that's probably the easiest assessment of the entire year. So it kind of balances out the first 2 a little bit. And then finally we have just one more after that that's, I don't know, somewhere in the middle, similar to maybe Chapter 4 last semester. After that, hopefully we'll finish that off around spring break, and then right around that time and up until your AP exam, we can focus just on reviewing only. So it's kind of what our semester will look like, and you definitely want to put in your best effort here at the first, and I promise to get a little bit easier after this 5154 stuff. So the first thing we need to do is the handout number 70, the one that says summation notation, and then it says arrows, definite integrals. So before we start to get into integration, I've mentioned since the first day of school, I think, that the first semester is almost entirely about derivatives. I know there's a few other things, but how to take a derivative and applications of derivatives. And for the most part, second derivative is about how to integrate and applications of integration. So just like with derivatives, we had to spend a little bit of time talking about how to take a derivative before we could really use it a lot. We kind of have to do the same thing with integration. We'll talk about how to do it, practice the computation, and then over time we will pick up some applications for things that can do. So before we use it, I think it makes sense for you to know where it's coming from, and this is a topic that they like to put on the AP exam. So this is number 70. It's the one that looks like this. So I need to, in these examples, try to show you through enough examples how you can take either this integral and realize that this stuff is the same thing, and or given this, be able to change it to that. We're going to try to change it both directions. So the first part of this is you need to understand what some of this is saying. So when we did Riemann sums last semester, we did like, I don't know, left Riemann sums, and one of the most important things for you to figure out is that the more rectangles you had, the more accurate it was. If you just do 2 or 3 rectangles, your estimation for area under the curve is not very accurate. If you did 50 rectangles, it would be pretty accurate. In calculus, integration finds us area under the curve, but not an approximation. It will be an exact value. And the only way you're going to get it to exact is if you have an infinite number of rectangles. So that's what this part is saying. We want the limit of the number of rectangles to approach infinity. Can't really have infinity rectangles, but we can approach it. Okay, and then this piece, this sigma notation, do you guys know what this does in mathematics?
Sum of.
Right, so this is sum. This will add up the area of those infinite number of rectangles. And then the rest of this stuff is easy because this is going to be in every single question. But the rest of this is like length times width. Since they are rectangles, length times width is what gives us the area of one rectangle. But if we add up all of them, we end up with an infinite number of rectangles. Okay, finding the width is probably the next easiest part. This represents the width of each rectangle. So for this particular question, it looks like we're traveling a horizontal distance of 3. So the width of each rectangle would be 3 divided by however many rectangles there are. there was 3 rectangles, each one would have a width of 1. There's 30 rectangles, each one would have a width of 1/10. But this is approaching infinity. So the fact that this means the horizontal change is 3, that's a clue to how you get this over here. 1 to 4, this horizontal change is also 3. If you start at 1 and end at 4, you are shifting horizontally a value of 3. Okay, so that's how you're going to come up with the width. This stuff, I'm going to highlight it for just a second, but all of this is essentially what changes over time. This is the x value. So this is like x to the 5th. And then the mess of this stuff, we don't necessarily want to start off at 0. So this you need to write in. This is the starting point. And that's how you would know that this is a 1. If we're adding 1 to this value, we're saying we want to start at this x value. Start when x is 1, so we're just physically shifting it that way. Okay, the rest of this, I don't know why this is defined this way, but this is how it's defined. They use right Riemann sums within the definition. So for the first rectangle, if I want to start off at x equals 1, I would go to 1, and then I need to go to the right side of that first rectangle. So I would add 1 multiple of the width. So k starts off at 1, so adds 1 multiple of the width. That's rectangle 1. Then this changes to 2, and so then this changes to 2, and then that would give you the right side of the second rectangle. Then k changes to 3, and then this gives you the right side of the third rectangle. And that keeps on going until you get to n. But since n approaches infinity, it just keeps adding those up over and over and over. So that's a lot of information, but again, just through process of elimination, we'll start to kind of piece these things together. So we're going to go in that direction on all of those first, and then we will reset and work those backwards. Okay, so question 1, I've got an infinite number of rectangles. I want to add up their sums together, and then I need to mentally think of this as like length times width. This stuff is the definition of an integral. So I can see that they're adding 2 to this value. So 2 must be the starting point. It's the first x value that I start to care about. Adding 2 shifts me horizontally in the right direction. The fact that this is a 3, this represents the horizontal change, the total horizontal change. So if I'm starting at 2 and it has a horizontal distance or length of 3, then this should be a 5. 2 to 5 gives me 3. And then this is the x stuff. This tells me what x value to start at. When k is 1, this gives me the right side of the first rectangle. When k changes to 2, it gives me the right side of the second rectangle. When k is 3, it gives me the right side of the third rectangle. So all of this is like x. So the thing that this is being plugged into is like this. It's f of x. It's just x looks really complicated. Okay. You also need to put the dx there. It'll take me a couple weeks before I can show you why the dx is necessary, but just trust me for now. It defines the variable. So this whole mess of stuff, this is not how we look at integration, by the way, but it is on your AP exam. In fact, I will even tell you that I do a quick little just Google form survey after the AP exam and ask people, you know, what things do you think we should have spent less time on? What things should we have spent more time on? And there was at least 2 or 3 people last year that said that they had wished they had reviewed this before the AP exam. So there must have been a couple of these questions on there. Of course, when it shows up on your AP exam, it's going to be a multiple choice, so that makes it a little bit easier. But just from a conceptual standpoint, we're going to be working with this integration symbol all semester, so it's good for you to see where it comes from. Okay, slide down to number 4. Okay, in all of that mess, what do you think the starting value is going to be? What's the first x value that I want to begin at? Good. The first is 0. Now, of course, they didn't have to put the 0 plus there because adding 0 doesn't do anything, but they're doing that for us here to make it a little bit easier to see. Does anybody have a guess on what the upper bound of this would be?
Pi.
Very good. So if this guy represents the width of each rectangle, the horizontal change is pi total, because you're dividing it by the number of rectangles. So if you're starting off at 0 and it has a horizontal change of pi, then you're going from 0 to pi. That's how you know that. Okay, all of this is the starting x value. Starting x value plus bump to the right side of the first one, plus bump to the right side of the second one, plus bump to the right side of the third one, etc. forever. So all of this is like x, and what that's being plugged into in this question is cosine. And since x is our variable, we need to put a dx there. Okay, on question 5, I'm going to pause for a second between the questions so that you can write in your best guess. Okay, I'd like you to look through that and try to guess what you think the lower bound of our integration should be. What is the first x value? Just put it on your paper. And you can change it if you need to. Okay, what do you guys come up with? I agree. We're adding 3 to multiples of the width, so they're wanting us to start off at 3. Okay, now take a second, and I'd like you to try to think about what the end bound should be. Figure out if you know what part of that you're supposed to be looking at, and make your best guess for a number. Commit yourself to an answer. Okay, did you come up with 5? Using this tells you how far horizontally you're going to change in total. So if you start off at 3 and you're traveling a distance of 2, you got to go to 5. 3 to 5 so that that horizontal change is 2 and you're starting off at 3. Okay, other than having dx, think about what you think the function looks like what the function is that should be plugged in here. Okay, anybody want to take a guess at that?
Square root of x.
Very good, square root of x. All of this mess under here is what is changing. All of this is the variable. Starting x value plus bumping from one rectangle to the second to the third to the fourth. As k changes, this adds another width of each rectangle. That's the whole thing. So again, as you feel more comfortable getting certain parts, the rest of it gets a little bit easier as well. Okay, looks like we need to flip over. I think we got maybe one more of these. Yeah. Okay, I'd like to do one more with you, number 8, and then I'd like to save number 10 for you to go back and do. Okay, so same thing, but this time go ahead and try all the parts that you think you can do. Go through there and try to decipher those pieces. And if you think you have the whole thing, and I gave you enough time, there are the answers on the bottom. So you can check it. And if your number 8 looks good, you can go ahead and start number 10 while I give everyone else another minute to try it. Okay, so I would start off by saying this goes from 4 to 5. And the way I came up with that is 4 should be your starting x value because that's what they're adding to each multiple of widths. Because this is 1, that's the total change that needs to happen. So if I'm starting off at 4 and it's got to change 1, this has to go to 5. And then all of this represents the length. This stuff in here is what's changing. This is like your variable. This is like what is x. So they're taking this stuff, multiplying it by 3, and adding 2. That's where they're coming up with that. The only other thing you have to put on there, mathematically this doesn't make sense without a dx. You have to define the variable. If we have x's here, then this will be a dx. If this was a u, we would call this du. Okay. Is there any, I know it's kind of hard to think of specific questions here, but are there any questions or any of certain parts of this you want me to go over again to help you see? Okay, then let's reset and go the other direction, which I think helps you understand it both directions. So go back to question 2. This is how we look at integration 99% of the time. But to know what this is saying and why it calculates the area under a curve, we need to be able to at least match this up with multiple choice. So now we're going the other direction. So I know I want the number of rectangles to approach infinity. I know I want to add those sums together. Start with k is 1 and go to n. And then I know, I'll put brackets here, that a rectangle is length times width. So those are the pieces I'm going to have to think about. The width's the easier part, I think. If we're starting at 1 and going to 5, the horizontal change is 4. So we're moving a full horizontal distance of 4. If you divide that by the number of rectangles, it tells you the width of each rectangle. And then for the length, we need to make all the change stuff be plugged in for x here. So this would be f of, just how this one's defined. This question has an f of, some questions have a cosine of, but that's going to determine that. And then what's going to change is I need to think about, well, what x value would you like me to start at? 1. And then I needed to bump from the right side of the first rectangle to the right side of the second rectangle to the right side of the third rectangle. So I need to do multiples. This is k. This is what changes over time. K is 1, then k is 2, then k is 3, times the width of a rectangle. That's how you move from one to the next. All of that represents our answer to number 2. But notice some of this is just an automatic. You know this has to be there. You know this has to be there. This part, you really only have to take the difference between these. Upper bound minus lower bound divided by n gives you the width. So that doesn't take too much. This part you need to slow down and be a little careful on. This x, whatever's changing, can be kind of complicated. Okay. So let's do that again with question 3. So I know there's some stuff that has to be there, like this. And this. And then I'm going to think about length times width. for the width, it's going to be something over n. What do you think that number should be? Should be 2. If you're going from 2 to 4, you've got a horizontal change of 2. And then the length, it looks like what we're plugging in is into sine x. So the length is going to be sine of x. X is the thing that we need to say, well, I want x to start off at 2, because that's the number they put there. And then to go from the left side of the first rectangle to the right side, and then the second, and then the third, and then the fourth, we need to keep adding multiples of the width. So k times the width. All of that is where this comes from. Now again, I'm not trying to dismiss and say that this is easy or anything. I think this is kind of tough to see. But the main thing is that you just feel like it's getting a little bit easier. There's more parts that you can find as we go along. Okay, let's look at number 6. So this time I will start to wing you off, but we know that's supposed to be there. I would like you to think about what the length should be and what the width should be. I want you to give it your best effort. Put pencil to paper. You can always erase it and change it if you need to, but I'll give you a minute to give it your best shot to see how close you can get. And if you're feeling really confident, again, you can flip it over, see if you got the right answer, and I guess you can start the next one if you are getting it. Your answer may not look exactly the same as theirs, but if yours is very close, then you'll be able to see why they did what they did. I'm still going to go over it. I'm just waiting a minute. Okay, so I think it makes sense to start off with the width just because it's a little bit easier. The width of each rectangle is going to be the total horizontal distance change. You're going from 4 to 5, that would be 1, divided by the number of rectangles. Tells you the width of each rectangle. Over here, this stuff is x plus 1 squared. So x plus 1 squared. X is the thing that's the variable. X is the thing that's going to change. The rest of that kind of carries along. So my first x value is going to be 4. That's where I want to start. And then to move from one rectangle to the next, I need to add multiples of the width. Now, if you look at the answer on the back, and certainly how this would be as a multiple choice question, they're going to combine the plus 4 and the plus 1 and call it 5. So, but same idea. Yeah. Does not have a K? Did they write it? They probably wrote it like, instead of k times 1 over n, they probably just said k over n.
Yeah.
Did that what they did? Yeah, same thing though. I know that you could figure that out on multiple choice. So. Okay, let's do one more, and let's skip the next one and look at the one after that because the answer is a little bit messier. So let me say this one more time, and then I'll ask you to go back and do the last two, the last one of each. So looking at this, again, I know this stuff has to be there. So that's just an automatic. I've got length times width to go from 2 to 7. The horizontal change is 5. Divide that by the number of rectangles to get the width of each rectangle. But for the width, and the reason why I wanted to skip the other one and go to this one, I didn't want this to throw you off, there can be multiple x's. So it's going to be 2 times x squared plus 5 times x. You can have x in more than one place. In this question, I want the x value to start near 2. So 2 plus, 2 plus. And then the mechanism to get it to shift from the first rectangle to the second rectangle to the third rectangle is to do multiples of the width. Multiples of the width. Now again, my answer looks way more complicated, and honestly I should probably put another set of parentheses here and here just to make sure that it shows that we're doing the sum of all that. Answer looks way more complicated, but I didn't have to like do any additional work. I just had to put that messy change for x in multiple places. So, but you can see down there in the bottom that that matches up. Okay, so do 3 things for me here. Take a minute, go back and finish number 10 and number 7. You've got the answers on the bottom. If you're struggling to figure out where those answers come from, you might put a star by it and try to ask me about it here near the end of class so I can help you. So do those 2, and then the last thing that you please, please, please take my advice and do this. Think of a sentence or 2 or 3, some hints that you can give yourself to physically write on the top of your paper, because even if you think you figured this out today and you feel confident with it today, again, we don't practice this skill again. Like if we end up putting it on your next test, I'll put it on the test review so you remember that it's a thing. But it's not something that we get to practice all semester long. So you're going to look at this in April when you're concerned about studying for the AP exam, and this is going to be intimidating. So give yourself a hint or 2, something that you don't think you might remember in the future so that you can figure it out. And I will wait just a couple minutes here, and if that's not enough time, you can go back in a bit. Just one more minute and then we're going to move on. Again, you can go back and work on it in a bit if you need to. make sure that you circle those if you don't have them finished, because you do need to finish those for the homework points on it. So, okay, next up we've got this one, 71. So unlike handout 70, where again I do think you will see 2 or 3 of those on your AP exam if it's like last year, and again I don't think it's easy, but if all those were multiple choice questions, I think you would think that they were easier than trying to write them out from scratch. That being said, this is the stuff that we will live and die by. So similar to like the first day we did power rule, product rule, quotient rule. This is kind of similar to that in the integration sense. Just kind of a big overview here. Integration, I don't know if I'd say it's easier. It does feel kind of tricky at first because it's the exact opposite of derivatives. We're trying to underive at this point. But the one nice thing about integration is there's a lot less integration types, at least at this level of calculus. So derivatives, we had to learn power rule, we had to memorize some, we had to do product rule, quotient rule, and chain rule. There was a bunch of different types of derivatives you had to do by hand. With integration, we undo power rule, which is pretty easy to do in our head. We undo the derivatives we have memorized. So assuming you have those memorized, just go in the other direction, it's not too bad. And then basically all the other types all fall into a process called U substitution. And U substitution does not come up on our next assessment, it'll come up on the assessment after that. So there's less types of integration that you have to worry about for this course than types of derivatives that you have to worry about. So looking at question 1, this is where you're given a derivative. Remember, this means derivative and this means derivative, so it could be written either way. And we are trying to backtrack and think about what function would give us that derivative. So you can kind of just do guess and check in your head. You can guess something, check it with the power rule. So what's a function that would have this as a derivative? X cubed. And we can check their answer by doing derivative. Bring the power down, lower the power by 1. That gives us that. Now, I tend to phrase this in my head because I don't like to do guess and check constantly, because sometimes I'm not doing a good job of guessing. So instead, with integration, you can say raise the power by 1 and then divide by the new power. So raise the power by 1 makes it a 3. Divide by the new power, 3 divided by 3 becomes 1. And then that process gives you a good starting point. Again, you should still always check it by doing the power rule. But is this the only function that has this as a derivative? Give me another function that would also have this as a derivative. Okay, plus 1. Because the derivative of this would be 0, right? So we wouldn't see that. Is that the only 2 derivatives, or only 2 functions that would have that as a derivative? Okay, what else could it be? I'm sorry, what did you say?
Any constant.
Yeah, basically any constant. Plus 10 still has this, plus 100 still has this, plus 300 still has this. So instead of putting a number here that we don't know, when it's talking about a general solution, you have to say plus C. Plus there could be some constant that we don't know what it is. So that's one of those things I will bug you to death about because it's pretty easy to forget about. So let me say that process again and talk about the checking. So in question 2, I have a derivative and I would like the original function. So I could raise the power by 1 and then divide by the new power. 1/3 divided by 3 would be 1/9. There could be a constant there, and probably forever you should check your work by doing the derivative. If I bring the power down, lower the power by 1, derivative of the constant is 0. You should be pretty quick with power rule at this point, so it should be a quick check. Okay, you guys okay with where this is coming from? Can move along? Okay. Alright, so when we talk about integration, sometimes it says like this, here's the derivative, what's the function? and then sometimes it actually used the integration symbol. But this is asking you to do the same thing. So figure out what the function would be so that if we took the derivative, it would give us 5x cubed. Again, this is just a different way to say it with math symbols instead of like, you know, a math statement, I guess. So we can raise the power by 1, divide by the new power, and there could be some constant there that we couldn't see. And then quickly check by taking the derivative. When you're just undoing power rule, that's all you should have to be doing, unless you have to rewrite it or something, if it's a harder question. So question 4, I could raise the power by 1, divide by the new power, and there could be some constant that we can't see, so we have to put the plus c. Bring the power down, lower the power by 1, and see that that simplifies to that. So for the most part, I'm not saying anything different than questions 1 and 2 other than saying that this symbol, that's what it's asking you to do. It's asking you to anti-derive, find the antiderivative. Okay, so those are undoing power rule, but what about this one? What can I take the derivative of to get cosine? Sine, very good. And what can I take the derivative of to get 8? 8x. And is that it?
Multiply by x. Add c.
Okay, just the plus c. And there could be a constant that we can't see. Now, I would say this one in particular can be tricky because you guys know from last semester the derivative of sine gives you cosine, the derivative of cosine gives you negative sine. Now we're flipping the process. So to integrate cosine is sine, and to integrate sine would be negative cosine, right? Again, that's going to feel uncomfortable for a few weeks. That's why you have to, before you circle an integration as an answer, just take the derivative. Derivative of this is this, derivative of this is this. There was a constant, it would be 0. As long as you're willing to do that check by doing the derivative, then you should be fine. You at least know not to move on too fast. Okay, there is one that's kind of different. So last semester I told you this one, the derivative of natural log of x is 1 over x. That's one of those we have to have memorized. And then integration is almost the same thing, but there is one little catch to it. If you want to integrate 1 over x, it's actually the natural log of the absolute value of x. When you're going this direction, you have to include absolute value signs. The reason for that is you cannot take the log of a negative number. And last semester, the direction that we went, you wouldn't be plugging in a negative number because mathematically that doesn't make sense. So no one's going to ask you a math question that doesn't make sense. But going this direction, if you don't put that, you may look like you're taking the natural log of a negative number, which doesn't work. So when we're going this way, we have to do absolute value sign. All right, so these are considered general solutions because I didn't know what the constant was or if there was a constant. So I just have to put plus c each time I integrate. There's also something called particular solutions, and this is the case where we can actually solve for what c equals. So our answer won't have a plus c at the end, it'll have more information. So what we can do is we're going to integrate. If this is the derivative, I can raise the power by 1, divide by the new power. Don't forget the plus c, and check it with derivatives. But sometimes they're going to give you more information like this. They're going to say, oh, by the way, when y is 8, x is 0. That gives you enough information to actually figure out how big c is, and our answer can be more specific. We don't need it to say plus c, we can say plus 8, because we actually know what c is with that extra information. Doesn't make it harder, just makes it, one extra step basically. So say that one more time. To go from f prime to f, raise the power by 1, divide by the new power. If you've got multiple terms, do the same thing. Don't forget the plus c. Check with derivative. But if they give you more information, like y is 7 when x is 1, then we can actually solve for c. This would be 4, so 3. And then when we write our answer out, instead of saying plus c, we can say plus 3. Now this goes through that point that they say it's supposed to go through, and he has the derivative that they say it's supposed to go through. So that's something that we do occasionally here or there. Okay, are we good with that part? Ready for the last piece? Okay, and then the last thing I need to introduce you to so that you can start to absorb all this and get practice in. Up here, these are called indefinite integrals. Indefinite, because these don't have bounds to them. It doesn't say to go from this to this or this to this. Right? There's no numbers on our integration symbol. But there's also called definite integrals, and we do have the bounds. We're going from 0 to 1, or from 1 to 2, etc. So here's how you're going to deal with that when that's the case. Well, first off, the integration is not going to change. You're still going to raise the power by 1, divide by the new power, raise the power by 1, divide by the new power. Integration is going to be the same. Now, I'm not going to do this probably at any other point the rest of the year, but I'm going to do it right here so that you can see why this works this way. There could be a constant too, but on a definite integral, when we have these bounds, you don't have to keep up with this plus c. And you're going to see why in just a second. So mathematically, we have integrated, but we still have to evaluate from 0 to 1. The way we show that is with this little bracket and the 0 to 1 over here. This is indicating that I've done the antiderivative, but I have not dealt with the 0 to 1 part. Okay, make sure you're paying attention here because this is going to go quick. All you do is you plug in the upper bound into this. And you get a number. Then you're going to plug in the lower bound into it. Get a number, and then you subtract those. The reason why you don't have to keep up with the plus c on a definite integral, you can if you want to, it's just you're going to be doing a lot of unnecessary work. Do you see how we have a plus c and then we're guaranteed to have a minus c as well? The c's are going to cancel out anyway. So, I don't know, whatever 2/3 plus 5 is. I don't really care to add those together, but that's the answer to that whole question. That's all you have to do if you have these bounds. Plug in the top bound, get a number, then plug in the bottom bound, get a number, and subtract those, and that is your answer. So, one more for your notes here. First, let's integrate. Raise the power by 1, divide by the new power, raise the power by 1, divide by the new power. You can put the plus c if you want to, doesn't matter on this type of question, but you do need to say this is from 1 to 2. This notation is important. On FRQs, they will expect you to show this at some points. Okay, honestly, the calculus part is now behind us. You plug in 2 into all of this, you get a number, 16 plus 10, 20, would be 36. Then you plug in the lower bound into all of this. you subtract those two. The c's go away, which is why it doesn't matter if you keep up with them on a definite integral. You better remember it on an indefinite integral, or if it wants a general solution, you're never going to know what c is, so you have to say that. But these always cancel out, and so then whatever this totals up to be would be the answer to that integration. So the hardest part is doing the antiderivative, undoing the power rule, undoing the things that we have memorized. That's the part that's going to require the most practice. This takes a little bit of practice too, but you can see it ends up just being arithmetic. Before we move on to the last handout of the day, I want to just kind of remind you the only application we've talked about with this thus far. Just make up a real quick example. We know what x squared looks like. If I ask you how much area is between the curve and, or the function and the x-axis between, let's say, 0 and 1, how much area is this? We can estimate that with the Riemann sum, but if we integrate, just like the first handout we did today, integration gives us an exact area because it's doing an infinite number of infinitely thin rectangles for us. So we could say, figure out how much area there is between 0 and 1 for this function x squared. And even by hand, all you have to do is undo the power rule, raise the power by 1, divide by the new power, evaluate it from 0 to 1, which means you plug in 1 the first time, plug in 0 the next time, subtract those, and then you know exactly how much area that was with pretty little arithmetic, all things considered. And that's significant. Again, if you guys are going to be engineers, if you're going to make things, most things in the real world are not made up of squares, rectangles, and triangles. Cars need curvature to them. For them to be aerodynamic, there's got to be some curvature to it. And you know, area still is going to represent the same stuff that it's always represented, but now with a little bit of antiderivatives, you can figure out exactly how much area you need, even if it has curvature to it. And it's not just an approximation. Okay, on to the last part. Or, I'm sorry, is there anything you guys would like to ask about this handout? Again, this is stuff that you'll be really comfortable with after a few weeks, but the sooner you let all of that clip, the easier things will be for you. Okay, then I would like you to do the other handout. So this is the circuit. All of these questions are fairly basic. I thought this would probably take the rest of class and maybe a little bit of homework, but yesterday I'd say most of the class finished this in class. But what they want you to do here, let's just talk about one example here, and I got to tell you one other thing, and then you'll have some time to practice. Here, they give us the derivative, and they're asking us to try to figure out what the original function could be. So, if I'm trying to do the antiderivative of this, raise the power by 1, divide by the new power, check by taking the derivative. For 3, raise the power by 1, divide by the new power, check by taking the derivative. I also could have a constant that I can't see go in this direction, so I have to say plus c. Now, part of why I'm doing this first question with you is if you look at the answers, none of the answers say plus c. They're going to just throw in a number there. Because again, this is kind of like for the first time you've ever seen this. This is real introductory. So c might be 1, it might be 100, it might be 500, but the box that has x squared plus 3x plus a constant x squared plus 3x plus a constant is the one that you're looking for. So that would be box 2. Okay, the one last thing I need you to write on your paper so that you can do these is there are 2 derivatives that you have not had to memorize yet, and you still don't have to memorize them for us. I will warn you if we're going to put it on your next test, but you will have to have it memorized for your AP exam. It is the derivative of inverse sine and the derivative of inverse tangent. When you get to a question that looks like one of those, or looks like you're not just trying to undo power rule or just undo something that we have memorized, look at the top of your page and make sure it's not one of those 2. Otherwise, the rest should go okay. Should go pretty smooth. And you guys have about 35 minutes. So again, I really think you probably can finish that up in class. Seemed like most people could last time. And I'll give you a few minutes to give some of it a go before I come around and help. I am going to ask that you turn in all 3 of these in the Google Classroom before next class. So, of course, if you have class time, it would be best if you just did it while you're here so you don't forget about it.
Google Classroom, please.
And of course, after a few minutes, if you're struggling with the first few, you need to work with your neighbor or call me over and let me help you. Again, this is going to be this just like derivatives last semester. This is kind of like the power rule of derivatives. This is the stuff you're going to be using all the time. You want to figure it out sooner rather than later. again, if you need some help or some hints, just call me over if I come around.
Yeah, you could, but then you're not practicing what you need to practice. Well, one of the two, when can you take the derivative of to get cosine? And the derivative, if this is 2 sine, your derivative would just be 2 cosine, you make it twice as big. So that 2 is gonna stay out. Okay, that's 2.
Is this your son? Oh, I'm not sure.
Now, actually, but what you were saying could be a strategy on like a multiple choice question sometimes, you know, if you need to integrate, you could just take all the answers and try to take the derivative of them, see how many they do. So this has one step of chain rule, so ignore this 2 for just a second. What could you take the derivative of to get cosine 2x? Just sine 2x. So write down sine 2x. And now, if we took the derivative of this would give us cosine 2x and a times 2 because of the chain rule, right? So that's where that 2 comes from. Bottom right? Okay. So, if the derivative of the natural log of x is 1 over x, integrate 1 over x, it's going to be the natural log of absolute value of x plus the, well, if x is a positive number, you can remove that. So, right. Yeah, 5 is just the random constant. So it's not like the one you made messed up with 2 cosine x. Box 5 or box 6?
Box 5.
Wait, secant square of x.
Come back. I'm not sure if you'll know where it is. Well, if I just ignore this, if I take the derivative here, the derivative of sine 2x would be cosine 2x. Right? That's good, I mean that. But because the chain rule is also multiplied by 2, you already got a 2 up there, so yours has a 4, and it should just be 2. So erase that 2. That 2 is going to be created just from chain rule.
For this one, I got the absolute max. One is for 7. These are my 2 options.
It says 1 over x, 1 over x plus
This is
1.
my guide.
So I would say the natural log of the absolute value is 1 plus x. Or x plus 1.
So, there you all go.
Plus the equal to. As long as it's not creating a chain rule piece, if it's just in the denominator, you can always try to make it log just that part. There's like 2 of these that have like 1 step of chain rule that you're trying to undo 1 step of chain rule in your head. So 1 step's not usually too bad. And of course you can ask me today, but just so you know, in the future, if something's really complicated trying to undo chain rule, that's what the U substitution process is going to be for. So that's for several weeks from now. You won't have to try to undo some weird chain rule multi-step thing in your head ever. Again, those of you that are it's clicking with and you finish up, again, I will ask that you have these in Google Classroom before next class. So just go ahead and just get them turned in. Well, when we take the derivative of e to something, we always get e to something, right? So let's go ahead and put down e to the 2x. We know we want e to the 2x. So now if we try with the derivative, this is going to give me an e to the 2x, but it's also going to create a 2 that I don't want, right? So if we put a 1/2 here, when you multiply by 2, it'll cancel that and make that 1. So if you put a 1/2 there, then that's what I meant by like I'm doing a chain rule. Sometimes you just have to write down what you think the answer is supposed to be, try to take the derivative, and then see how you need to adjust it.
So for this book, I showed it to my brother. He can't do this anymore. He said that. So these rectangles only have 4 edges, and these have 5. So however you draw the line, if you draw it to the 4 rectangle one, then the line starts outside of it. Then it also has to end outside of it. Because it's created with no edges. But if it starts inside, then it also has to end inside it. But if that's 5, it's
Why do you have to start with 5 now?
you don't have to. But if it has an even number of edges, then if you start inside, it'll also end up inside. Or if you start outside, it'll end up outside.
I mean, that's an interesting theory, but I can still do it. So.
Okay. So, but if it's 5, then that's the start, and the one end going to be inside it, and the other end going to be outside it. Because it has any positive edges.
Not if it's the last part you went to. If it's the last part of the puzzle, you started in there. Like, if I want to start the puzzle here, I can start inside of it, do this puzzle, and then still end in there too. And you can start ending in one of them.
Wait, no, because this has an on the 2x, so if you go through each edge, then you start inside it.
Okay.
So there are 3 lopsided shapes. So
Everything you're saying is great, and I don't know if I disagree with much of it, if any of it, but I can still do it. So.
like on a flat sheet of paper.
Sure.
It's impossible that my brother drew the edges.
Well, I'll tell you at the end of the year.
So, this is my 10, and I don't know if that's right.
Yep, that's good.
Okay. But, so like, this is what I got.
Yep, sure we are.
I'm not sure, like, which one you're at.
Well, here, the +1 is in the x, so this guy's derivative would be 1 over x plus 1. Your denominator would be x 1 over
Okay.
like this.
Yeah.
See these?
Okay.
The derivative of this is here, this is the one you want. I wish it had absolute value signs there because it does matter, but then your constant is 5.
Okay, so, okay. Thank you.
I just showed my brother thought about it.
Your brother is actually so
If you don't see any
All right, you guys still have 20 minutes. Again, if you don't finish in class, you should be pretty close. You shouldn't have much homework.
This is the question we're asking, like, we think this is the answer. Like, if you were given this to take the drill, would you feel like
Times the chamber. Or 2x plus 1 or whatever she said, yeah.
So this should equal to negative x plus 1, and then negative 2 power. Right?
So, well, this part's okay, we can get to that. Okay, so that part's this part, I see that it's got e to something, and I know what derivative, e to something is e. So I know this is gonna be an e to the x squared, so I would just write that down. And then I would take the derivative just like that, and then see how close it gets. So, no, that's all. So if I take the derivative of what you have written down, e to the x squared, is gonna be e to the x squared. Then because of chain rule, it's gonna multiply by 2x, so that's where the 2x is. So you don't want that to be part of your function, it's gonna naturally create a villain. What was the hardest one? 13?
Oh, yeah, that one's
Oh yeah, 14 is pretty bad. If you rewrite it before you that's not
It'll work.
Okay, you guys still have about 18 minutes. I'm not going to bug you for questions as much, but please ask what you guys need help on. Again, if you don't ask what you need to ask today, you'll be asking in a week or two, and then you're going to be playing catch up. So.
So that one was 11.
Oh, right, yeah. So I made a mistake, I started, like, I didn't write anything after this.
Oh.
So I wrote down 1. So
Oh,
like,
okay.
was, there's no 0.
So for you, number 13.
Okay, so the derivative of the answer is how g. So
Or
it is the
if you
derivative
raise
of
the
each of
power, because the power of
anything
the
that
So raise the power
So
of
they took it out of the